I believe. I think I could be wrong. I was really wrong.
Wait, I'm trying.
No, I think you're right about that.
Negative. Okay. Negative 2. Is that what you want? Did you get negative?
Just 2.5. But it's in the direction.
All right. So.
She's saying 2.5. No, it's true.
Here we go. Hopefully you said negative 0.25 kilograms meter per second. Good? Okay. It's to the left. Will the total momentum of the system be conserved in this collision? If you make the system cart A and cart B. Tell your neighbor why. Ignoring friction. Yes, but if it doesn't, you can ask me, should I ignore friction? Okay. Correct answer is yes, because there's no unbalanced external forces acting on objects in our system. Ignoring friction, normal force and gravity cancel each other out. Those are external forces. So let's see what happens. So this is rolling medium, this is rolling fast. I'll do it for the video, then I'll do it for y'all. Medium, fast. Okay, so they bounce off each other. Here we go again. Ready? Ready? Medium, fast. Okay, good with that. So, answer these questions, these 4 questions right here. A is blue, B is red.
Next.
All right, here are the answers. Nope. Sorry. Tell your neighbor why.
Why are they the same? They have the same amount of time.
How do we do? A. was going this way and then went this way, reverse this direction, was going fast each time. Okay. Why do they experience the same force? Newton's third law. They experience the same force for the same amount of time because they're simultaneously acting. Therefore, if you experience the same force for the same amount of time, both will experience the same change in momentum. Good with that? Now, final momentum after the system. Is still 0.25 in the negative direction because it was conserved. Okay. Now this next part's a little wacky. Here's what we're going to do. So this is the momentum vector diagrams. So you had 0.5 to the right, and you had negative 0.75 to the left. So the total momentum of the system is 0.25 to the left. Like you already calculated all those. We're saying the total momentum of the system is conserved. So the total momentum of the system is still negative 0.25. Now we are going to make up numbers for A and B, but there are some guidelines, some constraints. First off, it needs to correspond to what we observed. We saw A bouncing back to the left and B bounces to the right. The other thing that is going to guide our thinking is the total momentum of the system has to be conserved. So this momentum of A plus momentum of B needs to equal negative 0.25. So make up numbers. This plus this gives you that. Okay, I made those numbers up. Don't necessarily have to be the same thing, but this plus this has to end up being that. You good? Okay? So now, once you have that, I want you to find the change in momentum for cart A individually. So cart A's final momentum minus cart A's initial momentum. Put that there, and then do the same thing for cart B. Hopefully, what you discovered is they have the same change in momentum, but one is positive and one is negative. If you didn't, you probably messed up on the direction. Final minus initial. Good with that. So looking at that and then observing, thinking about, hey, what is the direction of the force acting on the cart? Which way was cart A forced? Which way was cart B? Which way was the force acting on cart B when they hit each other? When they collided. So cart A, when they hit, experienced a force that way. Cart B experienced a force that way. Good with that. So A experienced experienced a force to the left. B experienced a force to the right. Check this out. Coincidence? Nope. Because the net force acting on an object will cause momentum to change. Whatever the direction of the net force is, that is the same, will always be the same direction as the change in momentum. Good with that? Okay. So this experiment 1 kind of sets the foundation for the rest of this lab. If there's anything that you learned, is there anything that you're like, oh, is there anything that like you got wrong and then figured out why the wrong answer is the wrong answer and why the right answer was the right answer? Jot that down. Do a little reflection on this Experiment 1. What did you learn? The last thing you want to do is just go, oh, that's good, and then have no idea how to use that on the test. Each of these labs have a test-worthy question. Does that make sense? Like, they're just going to be pitched in a multiple choice format. But conceptually, you're going to be able to have to like think through this for the test. Okay. All right. Experiment 2. We're going to keep the red one at rest, and the blue one's going to come in. Okay, it's going to look like, and they're going to bounce off each other. Calculate the initial momentum of the system. Calculate the initial momentum of the system. Okay. We're good with that. Okay. So here's the result, or here's okay. Ready? Okay, one more time. Okay. So fill out the rest of the stuff on that lab. Sorry, on that experiment. That's exciting. All right.
how do you know it's
Which what?
but like that, but it was moving. That one was moving like twice as fast as that one.
But
Oh, but it started moving fast.
right, this guy was going fast. This one went from moving, stop, and then back versus this one went from rest to moving. Great question. Question was, how does change momentum the same? Did it how the forces compare? We don't know the value, correct? Right. They have the same force for the same amount of time. Welcome. Okay. Go ahead and make up some values. Make up some values. And then answer the question.
So, for all these equations, is the v, I can tell if it's speed or velocity.
Other velocities. All right. Correct answer. Which one has a greater final momentum, A or B? B. Because the total momentum of the system is to the right. And you've got something going to the left, you got something going to the right. The total momentum of the system has to be going to the right. Therefore, this has to be greater than this to overcompensate. So the total momentum of the system is to the right. This is a test-worthy question. Okay? And I'm trying to show you how to go through it so that you're like, boom, got it. Boom. Okay? Experiment 3. Okay, experiment 3 is a little different because we're going to use equal masses. And we're going to tuck the bumper away, and they're going to stick together because they have Velcro on them. Okay? What's going to happen when they come together at the same speed and they stick together? Okay, go ahead and what's going to happen? Go ahead and hypothesize. Thumbs up after you've hypothesized.
What? Oh wait. Yes.
Here we go. Oops. That's a good one. Yeah.
Wow, that was last one.
Okay. Okay. So go ahead and finish this out. Experiment 3. Mm-hmm. Cancel out because they're going in opposite directions. Good at that. Okay. Experiment 4. It's going to be the same type of motion, except this time all the mass is going to be, or like the extra mass is going to be on cart B. So they're still going to stick together, but all the mass is on cart B now. So they're coming together at the same speed. What's going to happen? Go ahead and calculate the initial momentum of the system and hypothesize what's going to be the outcome. Okay. You had a negative 0.5. Good with that? Okay, here we go. Same speed going in. Same speed going in. Okay. Go ahead and finish out that experiment. So finish out experiment 4. Tell your neighbor why B had a greater final amount of momentum. Everybody get the circles? I scroll up. Okay, why did B have more momentum afterwards? Had more mass, they're moving at the same velocity, and therefore the one that has more mass has more momentum. So here you have, no, 0.25 going to the right, have 0.75 going to the left. Total was negative 0.5. Still negative 0.5 for the total momentum. So afterwards, you're making this up so that this plus this still gives you that. Good? call that a day. Got a review worksheet over just momentum due tomorrow.